नमस्कार, मैं आरवी सिंह यादव और आप देख रहे हैं मेरा यूट्यूब चैनल आरवी सिंह यादव एडिटर। आज दयालबाग विश्वविद्यालय में जो नेशनल सेमिनार है उसका पहला दिन था और पहला सत्र हम आपको सवेरे का दिखा चुके हैं। उसमें कुछ गलती हुई थी हमारी, उसको हम सुधारते हुए ये आपको बता देते हैं कि यह सेमिनार 5 दिवसीय नहीं बल्कि 3 दिवसीय है। 25 तारीख को ख़त्म हो जाएगी। इस पहले सत्र में आपने गुरु महाराज को देखा, उन्होंने भी पूरा जो सेशन था उसमें बैठ कर के हिस्सा लिया और सब चीज़ों को निहारा और उनका एक विजुअल चलाया गया जो 2012 में उन्होंने विदेश में एक विश्वविद्यालय में दिया था। और उसके बाद आज अभी जो दूसरा सेशन है इसमें मिस्टर भटनागर हैं बेंगलोर से, उनकी पूरी वार्ता है और उसमें शायद कुछ और लोगों ने भी भाग लिया। मिस्टर कालराड थे, उन्होंने सवाल जवाब किए जो दिल्ली से यहाँ आए हुए हैं। और अब इस वीडियो को मैं आपको दिखाने जा रहा हूँ। तब तक आपने मेरा चैनल अभी तक सब्सक्राइब नहीं किया तो ज़रूर कर लें और वीडियो को लाइक करते हुए शेयर ज़रूर करें। देखिए ये सेकंड सेशन का वीडियो।
Policy is our objective ultimately is to find an optimal policy, and the optimal policy is usually the one that maximizes the value function, okay, and that is defined as the expected discounted sum of rewards. Now this is, as I said, this is one way of defining the value function. There can be many other ways. For instance, there is this notion of long run average reward, or maybe you are in a finite horizon setting, so you just look at the sum of rewards, or maybe you are in an episodic setting where on an episode by episode basis you decide what actions to play out and so on. So those define, depending on the problem that you are looking at, you can choose one of these notions of the manner in which you define your value function to be. Now the skew learning algorithm essentially is a basic reinforcement learning algorithm. It basically was invented around 92, and in this thesis of Watkins. And in this paper of Watkins with his PhD advisor Peter Dayan, this appeared in this machine learning journal in 1992. So what it does is that it looks at updates these quantities called the Q values associated with state action tuples. So the idea is, suppose you are in state I and you decide on an action A, then essentially you want to estimate what is the Q value or long run average reward that you obtain, let's say even in terms of the discounted sum of rewards that I talked about. So you want to look at what that quantity is given that you are initially in state I and you decide on an action A. So the update rule is this. So if you notice, there is no way that we are looking at the transition probability. There is no, so we just assume that suppose you are in state I at a point in time, you decide on an action A. Then this state, the next state, that is state J, is something that you observe. And then once you observe the state J, then you have a choice of actions to look at that are available in state J. And you are maintaining, let's say, a table, maintaining a table of values corresponding to each one of these value tuples, these Q values and so on. And then you look at the minimum, you select this action greedily. So it's minimum over all feasible actions of this Q and minimum of E. And then you subtract this quantity. So this is kind of what we refer to as a stochastic approximation algorithm. The nice thing about stochastic approximation is that even if you don't have access to the system model and you just have access to data, then the question is, can you get to the optimal solution using just this data? The answer is yes. This kind of an algorithm helps you do that. You can find the optimal Q values. It's just that you still don't know the system model by the end of this process. And the thing is that who cares about the system model? As long as I am able to tell you what the optimal sequence of actions should be corresponding to a given state and an action. And so that's important to keep in mind that the reinforcement learning largely works in that setting, wherein you don't have access to the system model, but you still do something with the data, and you can do something smart with the data. But it's not always the case that one can always get good solutions. The idea is that, see, the thing is that if you notice, you need to look at all of these. So you need to run this algorithm, you need to collect values of these state action couples, the few values corresponding to each one of these state action couples. And which essentially means you need to maintain a truth table where the number of states and actions is humongous. Let's say on the order of 10 power 100 and so on. You don't really expect to run all of this essentially 10 power 100 times from each one of these state action couples and get good estimates of the few values for the possible state action couples. And that's where one often resorts to this notion of approximation. So we try and approximate the few values using some approximation architecture. What is demonstrated here is a linear approximation architecture where, let's say, theta is your parameter and sigma I are like the feature vectors that is associated with state action couple I from I. And then the objectives kind of reduces. I mean, so instead of looking at rating all possible few values for every state action couple, you want to estimate what is the best value of theta. And if you are able to figure out what the optimum theta is, then you are restricting yourself to the class of a parameterized family of function, and then you are asking the question, what is the best parameter within this family? Now, if your family is rich enough of the function that you are selecting, so linear approximation architecture is still rich enough because sigma I is something that's still in your hand. I mean, it can be ideal on linear function in states and actions. For instance, it could be a polynomial. So sigma I could be some polynomial function of I from I. So theta would then, theta transpose sigma I would then be a high order polynomial, and then you are sort of saying what is my best fit within this family of functions. Or it can be a neural network, and people have more recently been adopting architecture, neural network architectures in order to figure out what the optimal parameters corresponding to such architectures are. So in that setting, few learning with function approximation essentially follows this kind of a rule. Okay, so this kind of mimics what it was doing in the case of the lookup table case, where you are storing essentially the few values of every single state action couple. It's just that now you are only updating the parameters theta. Okay, and once you update the parameters, you have the corresponding estimates of the few values for every sort of state action couple. So this has been applied quite a lot in many applications, but the problem is there are no valid proofs of convergence for this algorithm, and the reason is it tends to become unstable. And it becomes unstable because of the fact that even though there is linearity in theta in this algorithm, there is non-linearity that gets introduced because of this min operation. And so the algorithm tends to get unstable. So in some of the work we did, we sort of separated the time scales of this algorithm. We said that, well, because this minimization is inside here, inside this quantity, is multiplying this learning rate of step size, what we do is we will do this on a faster time scale. Right? I mean, do the minimization step on a faster time scale as opposed to the averaging that happens there if you run this algorithm. And that's what is in a couple of papers that we published later on. So so as I said, you separate the few learning into two recursions governed by different step size schedules. So there are two separate learning rates. There's a faster step size schedule that goes to zero at a rate slower than the other step size schedule which goes to zero at a rate faster. The reason is that if you have a recursion wherein, let's say, something like this, where Cn, consider two cases. One in which Cn goes to zero faster, another in which Cn goes to zero slower. So if Cn goes to zero faster, the effect of this increment is going to be very limited. In fact, it's not going to be so pronounced. And therefore, this recursion will be a slow recursion. It will give you a slow but steady kind of a convergence. On the other hand, if Cn is a smaller or is a larger quantity, it goes to zero slower. Then essentially this recursion will have higher increments. These increments will become more pronounced, and the algorithm will kind of wobble around the optimal that's the idea we take in here. We say that we separate the two learning of these recursions. On the slower step size recursion, we run the value of it, whereas on the faster recursion, we do policy of it. And we are able to show its convergence. And the important thing is that we can actually prove that there is such a convergence to converge. Here's an application that I will talk about. This application is related to optical streamline scheduling sensor networks. The idea is that let's say you have a certain territory where you have installed all these ad hoc wireless networks, wireless sensors, and each one of these sensors can detect movement that may happen. And let's say there is an intruder that is passing by, they wanted on this solid line. So the idea is that, well, because these are battery operated sensors, you have to keep switching on and off these batteries, these sensors in order to maximize their lifetimes. But at the same time, if you have an intruder passing by while the sensor was sleeping, then that's a bad situation, because you would like, ideally, the entire intruder movement to be monitored by the sensors. So which essentially means that if the intruder is here, the sensor should be awake at that time. And the rest can be sleeping. I mean, maybe this sensor will be sleeping while this is awake. So that the energy of this sensor is sort of preserved while this person is awake. So that's the idea. So here is essentially the broad objective that I mentioned. We would like to minimize the energy consumption of the sensors while keeping the tracking error to a minimum. But the problem again, as I said, the problem that arises is that we are now in the partially observed Markov distance of the setting. Partially observed because if you are passing by and if the intruder is passing by and there is a sensor that is sleeping, then that sensor is not going to detect the intruder movement, and so it will go undetected at least for a certain period of time while the sensor is sleeping and the intruder doesn't pass by. So it moves into a zone where another sensor detects it. If of course, assuming that that sensor is awake. So therefore, it's not a completely observed setting. It's not that state information is all the time available. It is partially observed. So the sensors can be either awake or they can be asleep. We assume that the sleep time takes values in this range, which is 0, 1, 2 up to lambda. 0 sleep time means the sensor is awake. You ask the sensor to be awake, so decide on the sleep time to be 0. If you decide on a certain sleep time, let's say you decide on 5 units of sleep time, which essentially means that the sensor will be asleep for 5 instants of time. But once you have decided, we will assume we will not tell the sensor. We will not suddenly say, oh, we will not wake up. We will only tell the sensor to decide on that on waking up after that instant, after that amount of time that you receive for the possible lapse. We will assume that the object movement follows a Markov chain with a certain transition probability matrix. And then, so the objective is we would like to make the sensors sleep to save energy, but at the same time we would like to keep maximum number of sensors awake in order to have a good tracking accuracy. Okay, very briefly, I'll just, because I don't have time, I'll just talk about some recent work. There's a lot of activity that is now directed in robotics and so on. So there is this notion of what has brought up is this reference-based reinforcement learning, and this also appeared in one of our papers recently, I think last year. So the idea is that one can train reinforcement learning algorithms using a certain reward structure, but the reward structure is something that is given a priori. Usually what happens is that one cannot, one usually does not have access to reward structure or design good reward structures if you are training some reinforcement learning agent on a very complex task. So that is where reference-based reinforcement learning helps us. So here is an example. So what is shown is, what you notice that here is there is a robot that is trying to learn backflip. And so the idea is it should fall while flipping backward. Now if you have a complex task like this, then the question is how do we design the reward so that the robot actually learns to land in precisely so that it does not fall. Now many times what people do is if you don't have a very good idea of what might be good rewards, you say well detailed complex exploration in a very complex space. And so in reference-based reinforcement learning, the idea is you want to learn rewards themselves on the trajectories that you see. You just run trajectories using some basic policies and learn rewards, the reward structure that improves on those policies. Because that also goes under the name of what we refer to many times as inverse reinforcement learning. Okay, so here's an example. Essentially, this is what we trained. So there is this on a UAV navigation system. Let's say there's a UAV or to learn the UAV to fly in this complex environment. And the idea is there are obstacles and the UAV must sort of navigate around the obstacles. It should be in the air for as long as time as possible, but it should not sprint an obstacle. So if you notice, after the training gets over, it still it is able to navigate around the obstacle. It doesn't hit the obstacle at all. So that's one good thing to observe. So this was the paper. There are many experiments. I'm just showing this sample. Just to illustrate that this is an idea that is very useful. Okay, some other ongoing work. We have been looking at some multi-agent reinforcement learning algorithms because particularly single-agent reinforcement learning has been studied a lot. There is also work in multi-agent reinforcement learning, but not so much analytical work. So we are trying to plug in some gaps there. There is a lot of work we have done in vehicular traffic control and then energy storage management and microgrids and so on. And again, there is some work we are doing, other work we are doing in robotics and gravity navigation, as well as some things around energy sharing sensors and things.
Thank you, Professor Patnaik, for that wonderful talk, giving some introductory lessons on reinforcement learning and also giving some applications of it. So the floor is open for a couple of questions. Okay, so Shalabh, I just have a question on your first part of the talk where you were talking about Q-learning with FA. So there seems to be a motivation to get a speed, I believe, introducing this approximation. So what is the typical speed up you get or you expect?
You mean in terms of the computation?
Yeah, in terms of the
computation can be amazingly fast. And the thing is that, of course, you compromise on the accuracy. And that's important to keep in mind. It depends pretty much on how you design your features, how you design your, what should be let's say, the dimension of this vector theta. So typically what happens is that your state action space can be of if you are in a very complex setting, it can be of the order of 10 or 100 is very easy to achieve, particularly in network situations and so on, like your communication network, wireless network, vehicular traffic network, and so on. You add nodes, it just blows up. Now the thing is, if you look at really the dimension of theta, so theta can be like 100 or it can be 1000, right? You don't really need to have a very high dimension of theta, and that can pretty much capture it if you have designed your sigma IA, the feature vectors, pretty nicely. So in other words, instead of running through 10 power 100 or also equations, if you just run through 100 of them, and you are doing essentially, basically this is telling us on convergence of this kind of an equation over 100 of these equations, you get to a Q by E. Now one can ask the question, how good is it? And that's a difficult question to answer. So in most settings, what we do get is we do get good performance as well. You cannot say for sure that that's the optimal one can do. But it does better than most heuristics. You can design very cleverly formulated heuristics, but then it does better. And one of the important successes of reinforcement learning has been board games, particularly in background recently, and then there is this chess and so on, wherein these kind of algorithms have been deployed. You just run this kind of an algorithm with a neural network architecture. So theta n are like the parameters of your neural network, and you sort of cluster them together and then learn those parameters. It becomes an algorithm. And then once you game playing. But they are now into this war games and so on, the video war games, which are extremely complicated to navigate and so on. Yeah. So the speed up can be enormous, even though one can possibly not be able to quantify, because the algorithm, if you have nearly 10 power 100 states, that won't even converge over months and years and so on. This will give you some good answers even in a matter of an hour or so. That's the important thing.
Okay. And this takes us to the end of the session for before lunch, and I'll hand over to Vasudha.
Thank you, sir. Now we have lunch for everyone. All the delegates and guests may kindly join us for lunch in the hall, in the dining hall, and all the student participants and contributing authors. The lunch has been arranged on the adjacent corridors and the back side of the lawns of this building. So please have lunch, and we will meet again at 4:30 p.m.
आपको ये वीडियो कैसा लगा ज़रूर बताएं, लिखें, अपने विचार भी रखें हमारे सामने। और बाकी आपने वीडियो में सारा सुन लिया। सेशन 2 है, अब ये सेशन तीसरा सेशन आज ही के दिन करीब 4:30 बजे से शुरू होगा। उसकी भी पूरी रिकॉर्डिंग हम आपको सुनवाएंगे इसी चैनल पर अपने पर। और मैं आपसे निवेदन करता हूं कि इस वीडियो को लाइक करते हुए शेयर ज़रूर करें। थैंक यू वेरी मच। मैं आरवी सिंह यादव।